It's a pleasure today to have Sid Nagel, Steinfreeler Distinguished Service Professor at Chicago. Sid is one of the heroes of condensed matter physics. He tends to work on unusual problems. He's best known, probably, for the coffee ring effect. You will know when you get a coffee stain of coffee, you get a ring around it. It has to do with flows. He investigated. He's worked on all sorts of weird things. He's known for working on weird things. Water droplets. Question is whether they splash or splat or bounce. He's worked on that. How they pinch off. He defined jamming. He founded the field of jamming and still leads it. He is so well known that when Bill Clinton showed up at Chicago, he greeted him with "Hi, Sid," right?
That was the president of the university said, "This is Sid," and the secretary to the president said to the president, "This is Sid." So that's how they got it.
That's not the story you told. The story you said that he was told to say Professor Nagel.
No.
And then he said, "Hi, Sid."
I never said
anyway. Okay. He got his bachelor's degree upstate at Columbia, his PhD from Princeton. He's the leader of the Simons Foundation Cracking the Glass Problem. I once asked him whether he does soft condensed matter physics. He does a lot of work on granular materials. He said, "Well, I'd rather fall on sand than on concrete." Good. He's a member of the Academy. He got the Buckley Prize 20 years ago. And he's going to tell us about memory-directed aging and nature's greed.
Great. Thanks, Paul. Great. So what I want to tell you about today is what we've been kind of working on. It's kind of the intersection of three ideas that we find kind of interesting, which is aging, which I guess we all are all too familiar with, memory, which we're getting less familiar with as time goes on, and greedy algorithms, which I'll tell you a little bit about that as we go on. And what I want to really be asking about is, can we exploit information that's left behind in a solid after we've treated it in some way? And so what I want to be able to do at the end of this is to be able to create new functions in a solid that is not easy to create in other ways. So there are three parts to this talk. The first part is I want to give you some background. And so roughly it would be a third. The first part is I want to say something about why we're interested in disorder, why we're interested in glassiness, and the idea behind this is that there are new laws associated with the fact that something is disordered that you wouldn't have gotten if you had an ordered system. And that's worth exploring because there's new phenomena in nature that we get to look at. And there's one example that I'm going to be telling you about, this independence of bond-level response. Then the second thing is that because I'm working with a disordered system, what I want to emphasize is disorder is completely malleable. That is, I can make different things from disorder because it's disordered that I wouldn't have been able to do if I had a crystalline system. And so this means that with this new physics of disorder, there are new design rules that you can come into play to be able to make something. And so this is the idea of tuning by pruning that I'll mention. And then the final thing is that this idea of directed aging. And so this is the newest part. And so this is the part where I want to see whether materials can train themselves to have the properties that I want. And so this is where the idea of memory and nature's greed is going to come into play, and this is what I want to be emphasizing. So the first part is this, the missing half. That is half of our world, which is really we want to start thinking about from a disordered state rather than the ordered one. And so what are the new laws that we want to consider? So let me just start off by trying to show the difference between glasses and ordered systems crystals. And so I show at the top these two images of computer simulations, one of a crystal, one of a disordered random jammed packing. And from that you can see, well, the structure is different between these two, but that's not particularly illuminating perhaps. The second row of things is perhaps more to the point in that if you look at a crystal, what you know is that you typically have very, very deep minima for the energy surface. That is, there are going to be some situations which, so one perfect crystal is very deep in the energy well compared to anything else, and so that's how this thing is going to form. And so once you have that perfect crystal, you're in a well that it takes a lot of energy to get out of. On the other hand, if you had a disordered system, you have a very much more complicated energy surface on which you're dealing. And so you have many nearly degenerate ground states, nearly equivalent ground states. And so the number of states that you have in here is not... One point. Okay. I get nervous by that. I mean, I might hit someone. And so how many do I have? Well, it's not just n the number of particles, it's e to the n number of ground states that I have. So it's really a tremendously large number of ground states that I get to choose among. And so the idea here behind all of this is somehow the glassy state, this disordered state, is much more adaptable. I can choose one of these many different ground states and have something very interesting happen that might not happen in any of the others. And so this makes it a particularly useful thing to deal with. And if I want to go from one ground state to another, there are many paths for training this thing. And so these are the two aspects that I like about having to deal with this very more complicated energy landscape. And so the question is, can flexibility be harnessed for novel behavior? And that's what I'm going to be trying to demonstrate for you in this talk. So how does disorder matter to the material properties? And so I told you already that, well, the material properties of this glass is some kind of random array of these. This is a two-dimensional solid, so random array of these circles. But I would say, well, look, if that's all it is, that's pretty boring. When I was a kid, I was told, the window glass behind me, that was different than every other solid I had, and I rapped on it, and it seemed the same as everything else. I mean, if that was it, and if the only thing I had to do was I had to take that glass and take it to a neutron scattering machine to tell me that, oh, look, they're not in an ordered array, but everything else was the same, I would say, well, okay, that's not a terribly interesting issue. The issue would be is only if that disordered array of particles does something else to the system. And so that's what I want to explore. So, and the fact is that there is much more that makes the glass different, or the disordered system different from the crystal. And I want to just explore a couple of those briefly with you today. So one of these has to do with the elasticity of a disordered packing. So I'll tell you a little bit about what crystals do, and then show you a little bit what the glasses do. And then the second thing, which is really somehow much more unique to a disordered system, is this idea of aging. That is, if you have a crystal, well, a crystal is a crystal. That is, it doesn't age. You've already in the global energy minimum of the thing, and it can't go anyplace. Whereas if you're in a rugged energy landscape, well, then it can always try to look for other ways down to lower and lower energies, and over centuries, perhaps this thing will eventually flow into a new state. And so that's this idea of aging. And so aging is something that is really specific to the disorder. So to start out, I want to say just a few words about jamming. I'm going to tell you about jamming in this one slide. Basically, And all the examples I'm going to be using really start with the jamming paradigm, but because that's a well-defined thing for us. A lot of what I'm saying doesn't really have to be from the jamming thing. It could have been from any other kind of disordered system, but I can't tell you that because I don't know how to look at all disordered systems, so I'm going to tell you specifically for the jamming case. So what is this jamming? And so it's somehow I want to get a rigid solid out of something which didn't go from a liquid and I cool it down and it suddenly crystallizes. And so if I do the first one, that's a well-defined process. You cool it down and this thing finds the a small little nucleus that's very favorable, and then that nucleus, if it's big enough, it starts to grow, and it grows throughout the entire system. So that's how nucleation and growth phenomena, first order phase transition, would take place, and that's how crystals form. I want to go to the other extreme from that. What I want to do is I want to take all the particles that I have, and I want to do this infinitely fast so that I'm not allowing any relaxation to take place. So the algorithm, and it's done on a computer, so it's an idealistic way of thinking about it. So as I take a box, it can be 2 dimensions in a square or 3 dimensions in a cube or whatever you want, and I put into this box a bunch of spheres at random. They can overlap, they're totally at random, and then I define a potential between these spheres. So if they overlap, then they will just push each other apart. And so these things will push until they don't overlap anymore. And if they don't overlap, they don't see each other. So we're assuming that there's, outside their radius, they don't see each other at all. But if they overlap at all, then it's just like a repulsive spring, which is pushing these guys apart. So that's the model. That's basically it. So we put particles in. If we put the particles in and we have few particles for the volume that we have, so low density, then the particles will all just push each other apart, and it'll be relatively uninteresting. These things can flow past one another. It's unjammed. Nothing interesting happens. If we are at too high a density, then these spheres are forced to be on top of each other. And if they're forced to be on top of each other, then they can try and move apart, but now it costs energy to do anything to the system. That is, they're all in mechanical equilibrium, that is, the total force on every particle is 0, but the individual forces from each of the contacts are all pushing, but they balance each other out. So in this case, it takes energy to squeeze the system, because now I'm making these particles move up against each other. And so it takes energy to squeeze it. It also takes energy to shear this thing. And that isn't as obvious. That has to be at the same place, but it is at the same place. So I'm just taking that for a fact at the moment. Okay, so this then becomes a rigid object, right? That is, it has rigidity. Anything I do to the external boundaries is going to try to return to where it started. So it's going to be what I mean by rigid. So in between these two things, there's a point that may depend on what configuration I'm at, but but there's a phi j where this thing is just at this jamming transition. And at the jamming transition, these particles are just touching each other. Any more compression would mean that they get jammed, they overlap. Any less would mean they're loose and they can flow past each other. And so this is the jamming transition, and this is a transition that exists at 0 temperature. And so this is what we would, so we will come back to a few things that happen in the jamming transition in just a moment.
Is this thing, they're overlapping in your diagram on the right? That means that they're on top of each other.
That's right. So,
yeah.
So the potential, they are repulsive springs, but they're soft particles, so they can push into each other.
Okay.
So I have 2 Nerf balls, right? I can push them into each other. They would like to be pushed apart, but if they are on top of each other, they can. I mean, and the force will be dependent on how much they're overlapping, for example. And so you can do all sorts of, I can choose all sorts of different potentials I want between these, And it doesn't particularly matter just as long as there's a repulsive interaction. Okay, so now I want to say just a few words about elasticity, just so that we're all on the same page. And so if I wanted to talk about these two things I've just already mentioned. One is if I take my sample and I squeeze it in all directions as I compress it, well, then that will cost energy. And the amount of energy that costs for amount of compression, that's a measure of what we call the bulk modulus of the material. So that's the first thing. So that's the bulk modulus. That's the energy by which it doesn't want to be compressed. The other modulus that I'm interested in here is the shear modulus. And so if I take the solid and I try to shear it in this direction, as I've shown up there, that will also cost energy. And that energy is going to then be a measure of how much it costs per unit shear, and that is what's called the shear modulus. Okay, so these are the two modulus, the bulk modulus and the shear modulus. And if you have a crystal, nearly all crystals have essentially comparable shear and bulk moduli. They have the same units, and the numbers are essentially the same. And why is that? For a relatively simple reason, is that if I have two particles and this interaction that we're talking about, they're pushing up into one another, well, they're going to be pushing each other apart. And so that what the bulk modulus is really measuring is how much it costs to have overlap of these particles. If I did the shear modulus, well, I'm trying to shear it this way, and yeah, they're coming in at an angle with respect to each other, but that's only a cosine theta. I mean, it's not an enormous factor, so maybe I'm off by cosine of something, and so it's a third or something like this. It doesn't have to be any particular number, but it's not going to be order of 10 to the 15. I mean, it's going to be something of order unity. And so in crystals, the shear modulus is always comparable to the bulk modulus. That's basically the reason. It's you're dealing with the same potential and you're just coming in at different angles when you try to shear or compress it. Okay, but in jamming, if you go to that threshold where the jamming threshold where they're just touching, then something rather nice happens, is that the ratio of G over B, instead of being some constant of order unity, goes to 0 at this thing. So what that means is that it becomes infinitely more easy to shear this system than it is to compress it. And so this says that, okay, if I started with this jammed system, it's really going to be much more flexible. Already we can see this in that if I compress this, it will cost a lot, but shearing it won't, and that's already different from the crystal. And if I compress it more, then I get towards the crystalline result. That is, so I can tune this ratio of G over B by many, many orders of magnitude. It goes to 0 at the jamming transition. And so this already shows this idea I'm trying to say, that disorder makes things flexible, something that we didn't expect from ordered systems. Okay, so now I want to just simplify the problem a bit for what I'm going to be talking about from here on in, which is instead of dealing with these spheres or circles in this case, I'm going to just think about this in terms of a network. And so I'm going to take each circle, I'm going to find its center. That becomes a node in the network. And I'm going to ask which particles overlapped with what neighbors. And these two particles overlapped. And so I replaced it by a spring between these two particles. So I'm replacing every overlap by a spring and every sphere by a node. And at the end, this is the network that corresponds to this sphere packing. And so it's this network that I'm going to be dealing with from here on in. Okay, so this is just when I'm talking about bonds, I'm going to be talking about these springs between these nodes. And these are unstretched springs to make life simple. Okay, so now how do I started off with this rough energy landscape. And I'm interested in understanding, well, how do I explore this rough energy landscape? And there are two ways that we've been taught to do this. One is thermodynamics. That is, I just raise the temperature or lower the temperature, and I'm able to then have thermal excitations across barriers that go from one well to another well to another well, and so that's one thing. The other way I can do this is by shearing the system. That is what's called rheology. This is by putting this thing under some external forces, I can move the system from one well to another as we go through. Okay, so those are one set of ways we can do this. But there's a third way, which is what we started to explore, which is I can go into this network now, and I can prune bonds. That's another way of exploring what is the nature of these minima. And if I can prune them, then I can begin to explore what those features are. And this is what I'm going to be talking about now, is to see what does pruning do to this disordered kind of system. So let me start off with the idea of how I'm going to do this. I've already introduced to you this idea of the bulk modulus. That's the energy it takes to compress the system. Suppose I go in and I take one bond I labels the bond, and I go in at random and I choose some bond I, and I remove that bond. I can then again measure what the bulk modulus is of this thing, or the shear modulus. And I see that, oh, the bulk modulus has dropped by a certain amount, delta B, depending on the bond I. So I get a value for delta BI. I then put that bond back, and I reach in at random and take another bond and pull it out. And I measure what the change in the bulk modulus and the shear modulus are for having removed that bond. And I can do this through all the bonds in the system. Well, suppose we started with a crystal. What would that have looked like? So what I just said is that every bond, so I'm taking the simplest model of a crystal, that is one atom per unit cell. So the simplest thing, what it would have done is that if I take out one bond and I ask what the delta BI, I put it back and I take out any other bond, it does exactly the same thing because all bonds are the same in the crystal. That one bond is the same as any other in talking about this bulk modulus. And so what that means is the probability of getting a value of delta BI is a delta function at that one value. So everything is situated right at this value of delta B. Okay? So everything happens there. And so that's what we get in the case of the crystal. And now the question is, well, what happens when we put disorder in? And if you're like me, what I thought was going to happen if you put disorder in is, well, you have a sharp thing like this, and it should end up looking like this. That is, it just broadens out that delta function and gives you maybe a Gaussian around that value of delta BI. Okay, and so this is this was my naive expectation, and so now what I want to show you is, well, what does the real system do? This real jam system, and it does this, and so you can already see that this is a log scale. So dirty work is afoot, right? That is, it's no longer not just a delta function, but this is an incredibly broad distribution. It goes all the way from some average value. They're all normalized by the average value. So it starts at 1 basically, and then is basically a straight line, power law, behavior, all the way down to delta B is 0 or delta G is 0.
After you cut the bond, does it relax again to a new ground state, and then you measure the shear?
Yes, that is. So what I've done is I take the bond away, and now I squeeze it and I look at what the new response is. I start off.
When you started with the ground state, it's in where the forces are balanced.
Oh, what I said is that I replaced in this thing. What I've done is I replaced the overlaps with unstretched springs.
Okay.
So that means that once I've cut the bond, it doesn't relax. And the question, it's a very good question of what happens when the springs are stressed, and I don't I don't particularly have a good answer for that. So, but this is where we're starting with this.
So the only thing you used from the Jan system was just a geometry.
Just the geometry. And so this is the distribution function, and what this is the real data. And what you see is there are actually a lot of curves on here, and some of these are for this probability distribution function for delta BI over its average. Others are for delta GI over its average. So what it's saying is it's the same universal distribution function for the delta B's and the delta G's. That is, it doesn't depend on which perturbation I did from the outside. It has that kind of a spread, and it has that kind of universal form. There's a little asterisk here that's sweeping something under the rug, but it's something relatively small. So basically, what I'm saying is essentially completely true. And then this very talented, smart postdoc, Daniel Hexner, was able to prove what this distribution function is, and it gives you y to the minus 1/2, that is, it's delta b to the minus 1/2 until it reaches the crossover point, cutoff. And so this is something that we can understand. We can measure that and see. And so this you have a distribution of bond level responses, and the distributions are broad, they're continuous, and they're this universal, that all have the same shape.
Is that a fit, that function, or
Yeah.
it's
No,
a
that is the analytic form that he derived, and the data is the fit. So what you should see is this kind of light blue dashed line. That's this curve. And so you see that's going through all of this data. That's a functional form that he derived. It's not fit to this. That's the form.
derived based on some fundamental principles.
And fundamental principle, basically assuming that things are random and not uncorrelated. Okay, so that's one important thing. The second thing about this is that I told you these are a lot of curves under here, and so I didn't change this at all. But there's another conclusion that you have here. That is, what I would have thought if I had started with this is, okay, so I have a bond which is really very important for the bulk modulus. Okay. If I take that bond away, I would have expected that it would have affected the shear modulus as well. That is, if a bond is important, it's important. That is, it shouldn't matter what perturbation I'm doing, that's the important bond. What this is showing is that is not the case. What it's saying is that if I take a bond that happens to be the largest bond important for the bulk modulus, it could have come equally likely anywhere in the shear modulus. That the contribution of a bond I to the bulk modulus and the shear modulus are completely uncorrelated, and completely, again, with the asterisk within 1%. And so it's really only a very small amount of decorrelation. So, of correlation. That is, they're completely uncorrelated with each other, basically. And so that, again, is a surprising result. Not only is it not this Gaussian around an average value, it's broad, and these things are decorrelated from one external perturbation to another. And so then this allows us to formulate this new independence of bond level response principle that I say is important for the disordered materials. And so what it's saying is that the contribution of any one modulus is uncorrelated to its contribution to another, and that the different bonds contribute differently to any modulus. So these are the two things that I want you to get from this. And this is a new principle that we've only gotten with this disordered material.
Do neighboring bonds correlated?
No. So there's the delta, so you probably can see that simplestly for shear modulus, that is, depending on what the angles of these things are, each of these different bonds will then have a different contribution to how it contributes to the shear. So it's not that's not coming into the into play
Actually,
here.
Sid, you may have said this already, and I missed it. So when you break a bond in a particular realization and measure the shear modulus, do you average the shear, that measurement over angles?
We do both. I mean, so in 2D there are two shear moduli.
Mhm.
You know,
Right.
and the simple and pure shear, and they are not the same. So the one shear modulus is completely uncorrelated with the other shear modulus. Each one is uncorrelated with the bulk modulus. And now, when so those are three different distribution functions that I can have. Each one is uncorrelated with the others. Okay. Okay, so that's the end of the first part. That was the thing I wanted to get to, is that this is a new principle of disordered materials. Now I want to talk about how this can be used to give you new design rules. And so this is a picture I already showed you before, which is the shear, how we define the bulk modulus and the shear modulus. And now I just want to remind you of one other thing that you can think about, which is dependent on those two things, which is what's called the Poisson's ratio. So if you have a material, and I take this material and I pull it, the typical thing that you're always think is going to happen is, as I pull this, it's going to get narrower in the center. You can see that happening here, or in this direction as well. And so that's the typical response, and nearly all materials have this kind of Poisson ratio, which is called the positive Poisson ratio. That is, it's just the amount of amount of strain in these directions compared to the strain along the axis I'm pulling. You can have a negative Poisson ratio material, which is something like this. And so this, if I pull on this, it expands in all directions. Okay, so this is, those of you who like the universe, this is the universe. So where universe is a negative Poisson ratio material. Okay?
Who pulled them?
Pardon? That's between you and your you and your conscience. Okay, so that's okay. So these negative Poisson ratio materials can exist, but they don't exist naturally very well. So what is the one example that you have typically of something that at least has zero Poisson ratio? Is the thing you're familiar with is cork for your wine bottles. That is, if the cork has essentially zero Poisson ratio, so when you push it in, it doesn't swell. If it did, it would break the bottle's neck, and then pulling it out would slip out all too easily. And so the idea is that you want negative zero Poisson ratio materials for some examples, and you would also like to have negative Poisson ratio materials, but they don't really exist readily. And so that is one of the things that will be what I'm coming to. So what does this have to tell you so far? Well, this Poisson's ratio, which is just what I was showing you, is just a monotonic function of the ratio of G over B. And so in 2D, it's, well, this is a curve in 2D. So when G is really, really small compared to B, I have an incompressible material that is, conserves volume as I pull or push on it. And so this is normal materials. But if I go to G much bigger than B, then I get a negative Poisson's ratio material, and that's considered weird. And because it's considered weird, I mean, you've already called me weird, so of course I like it. But it's also, the thing is that it's not that Poisson ratio is the most important thing in life, but given that it's weird, we'd like to be able to show, well, okay, this is something that we can now make that we couldn't have made before. So that's why I'm harping on it to some extent. Okay, so what does this have to do with what I told you about? Well, given that the Poisson ratio is just a function of G over B, what I want to do is I want to change this ratio, G over B. And from what I told you in the first third of the talk, is I can do that by pruning bonds of either delta G or delta B. And I can do that any way I want, But I can do it in such a way that if I choose the one that takes away the largest value of delta B, then this ratio goes down. G only goes down by its average value. B goes down by the most value it can. So this ratio is increasing, which means I'm moving in this direction and I'm going towards this negative Poisson ratio material. And so this is the data for that. So this is where we start. And now what I'm doing is I go in and I find the bond which has the largest value of delta Bi. I cut that out. And what that means is, so I have one less bond here, so I've moved over to the left a little bit, and this ratio G over B has gone up. Notice that this is a log axis, and so this starts at roughly a third or so, and goes up 10 to the 11 on this plot. And I do this over and over again. Each time I remove a bond, I remove the one that has the largest delta B. Delta G drops by its average amount, delta B drops by its most amount, and this thing just rockets all the way up. So I can make this thing incredibly auxetic, or negative Poisson ratio, just by doing this pruning algorithm, which now we're allowed to do because we've shown that that's the principle of how this independence of bonds work. I could have done this for any combination of those delta B's, and so this is showing that is, I could have taken away the minimum value of delta B. That means that the denominator doesn't change at all, but the numerator changes by its average value. And so this thing becomes more and more incompressible as I go to the left. Likewise, I could have done the same thing with delta G, minimum or maximum. And we can get each one of these things will force us to one of the regimes in between purely incompressible and purely negative Poisson ratio, -1 Poisson ratio at the other end. And we can mix and match these in any way you would want, and we can get anywhere within this whole range just by this idea of pruning. And so what I want to point out here is that this is a greedy computer algorithm. So this is where I get to tell you about what greed is in this case. So a computer algorithm is greedy if it doesn't try to look at all possible solutions and find out what the best thing it can do is. All it's doing is looking at the most advantageous thing at the moment. So it's going downhill in some functional space, and so I'm choosing which way do I go, which would maximize my response. And so that's, in that sense, it's a greedy algorithm, and we're just going downhill. And so this is a greedy computer algorithm. I'm able to make all of these things starting with any network that I have. Okay, so the question that we then want to ask, well, how general is this? So this was fine for this idea of the Poisson's ratio, but there's another whole class of phenomena which you could have asked about is, how about suppose I look at local phenomena rather than this global phenomena? And so what I'm interested in here is an idea that we're borrowing or mimicking biology, which is this, what's called allosteric proteins. And so the case of allosteric proteins, it would be the following, is that I have a big protein molecule, that's this big thing here, and if this thing is not bound here, this hole over here is too small to accept this, to bind over there. And so it can't bind, the orange guy cannot bind to this protein. But if this binds first over here, it pulls this in and somehow opens this enough so that this molecule can now, the substrate is called, be bound over here. So it's basically this action at a distance, which is very important for protein regulation. And it occurs in lots and lots of proteins. And the question that we want to ask is, well, could we mimic this in these networks? And so the idea is that we take a network of the kind that I showed, and I take, so the way this goes is the following. I mean, I give you a network, and I ask you, please come in and choose 2 bonds at random that you want to be the source. So you came and you chose these 2. And then I said, oh, before you go away, come in and please tell me 2 bonds that you want to be the target. And so now I get to use this. And you chose those up there, far away, so as far away as possible. So you have perfectly, it was your choice, all of those things. And then I asked you, well, if I pull the source apart, do I want the target to come apart, or do I want it to come together? Okay, and so this is, can we tune in this unique and varied function, right, in this thing? So is that possible to do? And so this is what I want to show you is that here is an example of this. And so here is a network of this kind. So we here is all of these bonds, and they're connected. And I asked you to please choose one. And so what you happen to tell me, I mean, you can't do it now because we have to, but I mean, the computer did it randomly, and we did it many times. So these were the source here, and you chose these two things here to be the target. And then I asked you, you want it to be open or closed. And so what I really have here are two networks on top of each other. So you can see that they're almost the same, but you can see that there are a few changes between one and the other, where a bond on one is taken away, but not on the bottom one, and likewise bond on the top. And so now, if I do this, and I'll look at these two things. So these were the two containers. So now if I take this one, and I pull it apart, that one goes together. And if I take this one, and I pull it apart, it comes apart. So I can do this with nearly 100% confidence, being able to do this every time for these kinds of systems by removing relatively few bonds in the system. I don't have to remove much in order to create this kind of phenomenon. Now what I want, and so I should just point out, so this was also done at the same time by one of your old favorite people, Mathieu Biard, so also used to be from here, so he also did something very similar to this. Okay, so you can ask the following question, well, how complicated can I make this task? So I asked you to do one thing and one thing, but I could also ask you to suppose I have one source and I give you 3 targets. And I want you, by moving this apart, I want those 3 targets to do precisely what I want. And the answer here is, again, yes, I can solve all of those. Could I do it for 4? Yes. 5? Yes. 6? Yes. But then at some point it says, I can't do this anymore, and it just gives up to the ghost. And so this is the probability of success, depending on the number of targets that I'm asking it to prune, to control. And you can see that as the size of the system increases, the number that it's able to store also increases. And so as you go to a larger and larger system size, it looks like I can control an infinite number of targets, although the fraction of targets to the number of particles in the system need not be going to a finite number. That can be shrinking, but it's still controlling a lot of things. Yeah?
So when you say a target, is it just the direction, like expands or shrinks, or is it there's a minimal magnitude?
We're talking about minimum magnitude as well. Okay, so what this also means, because I can tune more than one thing, if I only asked you to tune one, well, if I was able to tune 2, I could have bet that second one any place, so that would have given me n ways of tuning the first one. If I can tune 2 others, there's n times n minus 1 ways of tuning the first one. So what it's saying is, in order to tune only one target, I can tune this in many, many, many different ways, some factorial number of different ways. And so this is why this makes it so easy to tune just one. There are many different pathways to tune just one. Okay, so what are the lessons learned from this? Well, the pruning works, but the problem here is that these are relatively small networks, and if I want to have a really, really, really big network, then I have to have a big computer to be able to do this simulation to get it. And also, if I want to work at small, go down to the atomic scale and do something, then I have to have tiny little fingers to get in to prune my bonds at that tiny scale. And so that's a problem. So that's why this is a very nice thing to do for large-scale objects. And so what I like to think of is that architecture no longer has to be rectilinear walls. We have lots of Frank Gehry examples which are all different ways. And what this allows us to do is take the struts of Frank Gehry building and prune in such a way so that if my colleague across the hall is irritating me, I can just tweak my window and his window falls out. And I just find that a delightful example of how science can be used. And I should have just pointed out, and we can do this in 3 dimensions as well. So there's a 3-dimensional example of that. Okay, so now what I want to say is, well, okay, so this is part 3. So what has directed aging got to do with this? So aging is typically considered a nuisance, right? And we think of it merely degradation, and certainly, as we get older, we certainly feel that coming along. Okay, but one example of that is, so here I have a ruler, and so if I had a ruler, so this happens, in high school when we had these plastic rulers, and I measured something in high school, and I got a value of a certain amount, and then I went home and I tried to reproduce it, and I used my ruler at home, and I got a different value. And the reason I got a different value was, well, rulers, the one at home was a little bit older than the one in, you can't see that.
Should I black this?
Oh, yeah. The one at home was more aged than the one in school, and so it shrunk over time, right? And so now I think they're better than that now, and so this was a little bit of a doctored example. I've aged this in a creative way, but this is the example. This is kind of what aging does in our.
Cook the data, Sid.
Pardon?
You cooked the data?
Yes, you're right, it was in the oven. But not very hot. I mean, so this was all below boiling water. I mean, so you could do this with just boiling. So if this had been sitting in the sun, we could have done the same thing. Okay, so what I want to now say is, well, maybe we can use aging in a better way than what what that kind of shows. And so I want you to consider the following example. So suppose you have an enormous pile, and so this could be sand, salt, whatever, and so this is some salt pile. And I want to look at what's happening deep inside this pile. And deep inside this pile is enormous pressure from all the weight on top of it. And so this thing is really coming down everywhere, a lot of pressure. And I want to look at what's happening between 2 spheres in that pile, okay? And so at some point, because the pressure is so high, some of these contacts under are a lot of compression, and they are really pushing up against each other. So like in this one. In another place, the compression is hardly there at all. There's hardly any compression at all. And so what I want to assert is, well, the ones that are under a lot of compression are going to be aging in a different way than those that are under no compression. Okay, and so here I'm trying to use the aging. The aging is kind of the idea that you're supposed to take from this is kind of like that pruning that I did. I pruned according to how much stress something was under. Here I'm letting it age depending on how much local stress a contact has. And so after a long time, the contacts under great stress deformed plastically, so they were under great stress. And so either the spring constant can vary in time, or the equilibrium length can vary in time. And so that's going to relax. Whereas the ones that are under no stress, there's no force trying to make them do anything, so they just remain the way they were. So this is a preferential relaxation of the stress bonds, just as in the case of the pruning. And so the system evolves depending on the stresses to which it was exposed. And so this is where memory comes in. So it knows how it was exposed to the forces in its past life. And the question is, does it naturally change its elastic properties? Auxetic is just another word for negative Poisson ratio. I shouldn't have used that. So does it become negative Poisson ratio? So this would argue that, yes, this sand pile, over time, much to our surprise, would slowly be becoming something different from what we set out when we first put it. And so you could say, well, sand piles that were sitting there for a long time can have different elastic properties than we thought, which might be problematic for, if you build a dam, for example. So how do we think about this? So we're going to talk about evolution under stress. I told you the two things. That is, the energy of a network that I have is just the sum of the energies on each of the bonds. What I'm going to do is I can either change the spring constants in time, just saying the spring constants are going to vary according to what the energy of compression is on that spring constant. Or I could say the equilibrium length of that bond varies according to, and time according to what the stress is on it. So those are two possible things. And I don't have to use a computer anymore. I mean, I'm letting the system figure out, okay, now it's going to evolve without my having to do any computations on this. It's just going to figure it out by itself. I'm under stress, therefore I'm going to relax. If I'm not under stress, I'm going to remain the way I am. And so this is the idea behind this. And I don't need any tiny fingers to do the pruning. And so this is a simulation by Daniel Hexner of what happens with the Poisson ratio. As we watch this thing aging over time of just this model, we started with a network, and we let this thing evolve, just varying the spring constant over time. And you see it starts off from a relatively large positive Poisson ratio, and it goes pretty negative. So we're able to make this auxetic material by itself, if the simulation works. And likewise, if you wanted to do the allosteric, this is harder to do. So what he figured out is, well, if you oscillate these two springs back and forth, back and forth, back and forth, the source and the target, at the beginning, the source and the target are not coupled, and slowly over time, as this evolves, the red is what's happening at the target, and that becomes to be on the order of 0.8 what the stress is the strain was on the source, so that you can also train this thing to be allosteric.
In the previous slide, I think you evolved K, and here
Yeah,
you
that's
evolved
right.
L naught.
Right, I'm trying to show that we can do it with either one.
But the purpose was different.
And I could have used L naught on the other one as well. To be honest, the way we use one versus the other, we don't have that completely figured out yet as to which is the most optimal one to do. But it's but we can try and study this in experimental to find out what experimentally is the system doing.
Were you doing it to all of them? I had the impression in the previous example that all of the bonds or all of the distances were behaving the same. But here it looks like you're picking two targets, or I'm
Okay.
confused
So
about
what I'm doing, in this case, I was just doing the compression. Under compression, I'm letting the system evolve so that I'm trying to make B as small as possible,
Right.
so it's going to go to that auxetic limit. So all the bonds are doing it. In this case, if I oscillate the source and target, all of these things in the middle and everywhere are going to be stressed by some amount, and the amount that they get stressed are going to be evolving in time according to that particular rule. But
Sorry,
we do know that we could have done it with the K as well for this, but which is better?
It was the source and target which just got picked out
Yeah.
because those are what you're oscillating. I had
Yeah.
to pick that up.
Okay, so then we want to demonstrate this in the laboratory in the same way that we want to demonstrate these these allosteric materials. So we take a variety of these different things. We cut these out of an EVA foam, And then what we do, so this is the unstressed system that we start with. Then we take a form that's smaller than the original, and we squeeze the thing and sit it in the foam, and then just let it sit. So we're doing nothing to this except let it age under that compression. And we let it age for different amounts of time, and under different compressions. We can do either one. And then we ask, well, what does this thing look like? And so this is what the data looks like. So that as a function of time, if we compress it by just a tiny little bit, it doesn't, the Poisson ratio doesn't change much. But as you increase the amount that you're compressing it by, this thing becomes negative, and for 30% strain, it becomes quite negative indeed. This shows what happens in all these different other examples. So the case of the circles, it doesn't go negative yet, but it's still a drop, and these other ones are able to go negative. So it's a demonstration that this idea can be used to create materials that nature doesn't typically provide us. Another.
Why wouldn't nature provide this? It seems like
I'm sorry?
it seems like this should happen all the time. I mean,
Yeah. So the question is, so what?
rocks or whatever.
Yeah, that's just, so one of the things that I love about this is, okay, so now I can go out and search in nature and figure out, can I, by reading what the material is doing, can I back out what the history of that rock was? So it's suggesting that something like that could be a tool that we could begin to use. The last thing I want to show is, so this is something that we came from here from. I mean, so we started learning from Dave and then Paul's work about shearing a system and watching how that system then evolves to become periodic in its behavior. There's a shear back and forth. That was for non-Brownian suspension, so they weren't interacting with each other. But you can also do this for jam systems and shear it back and forth. And what is totally surprising to me, I don't get it at all, but it is the fact that after a few passes, this thing suddenly gets into a periodic state. And so this is an example of that from Vrentovich's work. But so here you just jam the system, and then we start shearing it back and forth. So this is one cycle. You can see it goes over many different barriers as it goes pop, 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 and back, and ends up in a new place. You do it again, it happens in a new place. Third time, it happens in a new place. Fourth time, new place. Each time it's going to somewhat little different. But after the fourth time, it already is completely periodic. Because after the fourth time, fifth time, sixth, it's doing exactly the same thing over and over again. How the system knows to do that, but it's an example, I don't know, but it's an example of this idea of the ease with which this rugged energy landscape can be malleable, can be formed into a state that actually does something that you may or may not want, but this is something, a case that it can indeed be done. So the training is easy. I just showed it to you for the oscillating strain. It only took 4 examples in that case for this thing to find we started a random place and it finds a periodic cycle. And the tuning by pruning is what I started off telling you about. I only have to remove a few bonds and this thing was able to find the new state. So disorder matter is indeed malleable. That is, it can make into many different things. And so to conclude, I mean, so directed aging shows the malleability of matter. It's using nature's greedy algorithm. That is, nature is just going downhill and finding out whatever it is that it's under stress, and so I'm going to relax that stress. It's a local effect, so it's a greedy algorithm locally, and I don't need the computer to do it. It detects the landscape, and it goes downhill, and therefore it's directing the aging. It's directing the aging in a direction that we want something to happen in. So if we know what we want to happen, we can back out what the stresses are we should train it under, we can make that happen. It has a memory of aging that imparts function in situ. That is, it didn't have to be designed ahead of time. Now, I guess I have to always end a talk with, saying, well, no good talk ends without the bullshit line. Okay? And so here is the bullshit line. And so I hope everything above this you believe, because it's data, and here on in, that's up to you to believe. But it's kind of what we think is the story we want where we want things to go. And so there's this wonderful quote that I like from the choreographer Twyla Tharp from her book, The Creative Habit. It says, "There are as many forms of memory as there are ways of perceiving, and every one of them is worth mining for inspiration." And I think that's a beautiful quote. I mean, it really says, okay, that's kind of what we're doing. There's all these different things that we want. Maybe we could use different kinds of memories in each of these cases to gain us into one of these different places that we would like something to be formed. So that's the idea. And you know what? Below the bullshit line, so I can say it, we're limited only by our imagination at this point. I don't know where the ends of this would end up. It looks to be quite flexible. We can design for many different goals. It's scale-free, so that I can do the architecture, making my colleague behave himself, or I can do it at the atomic scale. I mean, so that's what we get to look at here. We can imitate biology. That is, we're using we can not only do this allosteric, but we can use tricks that biology uses to cut bonds in under the most stress or under the least stress, and that's exactly what we needed to do for this kind of the allosteric reactions that we were talking about. And again, coming to your last question as well, these memories are encoded all around us, and this directed aging really seems to be ubiquitous. And so, you know, where is it visible in our life? And so, can we go back and redecipher all of that? And so with that, I just wanted to put up the people who actually did all the work. Their names were under the bottom of all the slides that they were doing, but Andrea Liu, who I think many of you know, I mean, she was involved in every aspect of this. And so Carl started some of this work. Irmgard was also started with the experimental part, but the people who really did the heavy lifting on all of the stuff since were Daniel Hexner, my theoretical postdoc, Jason Rox, who is Andrea's theoretical graduate student, and Nidhi Pichini, who is my experimental graduate student, and she's the one who actually got all these things to work. And then the work on the multifunctionality was done by Eleni Kadafori and her postdoc Henry Brunellen-Stitch, and so these are the people who did the work. With that, thank you very much.
I'm glad we got to the bullshit line. Let me turn on the lights. Questions? Yasna?
So I have a question about allosteric. So normally you think about proteins and talking to themselves through this network of bonds. And so you're saying that if you do this algorithm, it tells you how you can learn about which bonds to remove in order to make the allosteric interaction that you're interested in.
For a mechanical network.
For a mechanical.
I don't want to pretend that I'm doing something for biology here.
I understand. But what did you learn about the design of that network such that you would have that allosteric response? Like, intuitively, you would think it has to be somehow related to jamming, in a sense that if you're in an isostatic limit, then you can, you know, transmit your stress from one end to the other. So should we be thinking that in the bits that you have the source and what did you call the other one? Target. Then those have to be near to the jamming point?
No,
whereas
they don't.
Things that are in between can be whatever they want? Or
The
you
things
need-
that they, so look, what I told you about is all things designed starting from jamming.
Yeah.
Because that's the well-defined starting point that I know how to deal with.
Okay.
I don't think that the main thrust of this is relegated just to jamming. There's, I think, lots of disordered systems could have this. There's no reason that it had to just be jamming. So, but I don't know the scope of that. I mean, I'm sure you can design things that don't have it. So I want to be careful about
But
what's
is there
there.
something that they do need to have that you do know they need?
Well-
Like a minimum of contact number 4 or a
Yeah,
percolation?
so I
or
needed,
something?
that is, in order for this thing to be rigid, I needed to be above the Maxwell counting limit. This has angle bending, so it's a little bit more complicated than just 4, but
Okay,
basically.
for the whole network?
Yeah. And then the thing is that what you can see here is the way this one is working is, you notice this part is kind of rigid. This part here is kind of rigid.
Yeah.
And so what it's doing is figuring out how what path to go between the source and the target to do this leaving rigid thing. So that's the simplest thing. But we could have also had this thing where this breaks up into many more little rigid regions which are doing this. And if I wanted this one to move 10 times more than this, I can do it, but I need more, I need to do much more flexibility around this one.
Right.
But these were not started near jamming. These were above jamming, so I have lots of bonds. And
But would you say that the question of the principle of design is still open then, in terms of what might be a rule for designing this thing without running your algorithm?
Well, so the algorithm is pretty general in the sense is that what we, basically the way, if you think about what we did with the making is negative Poisson ratio thing, what did we do? We just asked, okay, so which bond is contributing more to B than G? And then we cut it. I mean, so that's a pretty simple algorithm. I mean, it's just going downhill. It didn't need a whole lot of thinking, and that's why I like it, because that's my shortfall. Is that? And so I like that idea, and so this is kind of all that I needed for that. In this case, it's a little bit different, as what we designed here was we said, okay, if I stress this by some amount, I can ask before this doesn't do anything, and I ask, okay, so which bond, if I removed, would make this a little bit better? So this is, I'm giving energy functionals to, or a target function, and I'm asking how close do I get to the target function on removing things, and I just go downhill that way. So it's not a very subtle algorithm.
It's more like machine learning.
It's just, it's just saying, I can do this any way I want, basically. So that's, I don't know, is that?
Yeah, that's good, that's good. That's what
Your distribution is a kernel of the gamma function. I just Googled. So if you take an integral, it's gamma of something.
Yeah, that's how the.
Oh, that's how I got it.
It's basically it's a. That thing is the a Jacobian of this, something that comes into it. That's why you get that that extra factor. So that was how that comes about. But yeah, it's that kind of. You're starting with something that's Gaussian. Let's go away first.
If you have a system which is very easily tunable, isn't it also like easily untunable? Like if you make your network and then you accidentally snip a couple of the bonds, like could you sort of lose your property? So is maybe this is more of a philosophical question, but isn't that also a flaw to be so tunable?
Okay.
Like how do materials have robust properties?
Okay. So
given this?
you noticed that I didn't hand this around. And I've made the mistake of handing things around. I brought a whole bunch of these little things that I handed around one thing, and they came back all broken because people just couldn't resist pulling on them. I mean, I couldn't believe. They're all theorists. I mean, and so, but the fact was that even though I could see in a lot of these things that there were a lot of bonds that were broken, it still had the functions that we wanted in a lot of cases. So the answer is, once we've gotten something done, and I now do breaking bonds elsewhere, it's not clear, it's certainly robust to a certain extent. It's a very good question, that is, how robust is robust, and that we don't, I don't have any way of telling you exactly how much I need to, how many more I could tune without it falling apart or something. But
you're snipping some like really unusual bonds, I guess.
Yeah.
If you snipped average bonds, you wouldn't get instructions.
Yeah. That is, so if I snipped average bonds, I wouldn't get anything close to what I want. So I had to snip those bonds. And once I've got those bonds, snipping a bunch of other bonds doesn't change the action too much. But I'm sure that there could be some bond that if I did snip it, it would make this thing very unhappy. And so, so it's robust to lots of things, but probably not everything. And exactly how to mathematize that and say something concrete about how robust it is I don't know how to do that yet, but that is a good question.
Come on, let's get all in that.
Another material with a low shear modulus and a Poisson's ratio close to 1/2 is rubber, and there the structure of it is a polymer, and so it's very different type of molecular interaction that causes that. Can you get, despite that, can you get some similar mechanical properties using rubber that you get your model?
No, well, this is kind of a rubber that we're starting with. So these were a big sheet of rubber that we then put on a laser cutter, and we cut out everything that didn't look like a network, right? And we cut out the ones that we were told to by the computer to which ones didn't go. And so there are various tricks to this, which is what I should kind of, is that if you notice this, these things are thinner near the nodes because I don't like to have bond bending. Bond bending is bad for tuning things. And so by making it this way, we're able to show you stuff in your face that it really works. But if I put in, if I had very, very strong angle bending things, this would push it into a different class. But this is rubber. And so this would have been, if I had taken the sheet itself and pulled on it, it would have been essentially incompressible. It would have been a high Poisson ratio material. Yeah. So this did not start with anything that was, you know. I don't know, is that answering your question? Am I missing your?
Well, I think I'll ask afterwards.
Ask during the line. Is there any urgent question? Otherwise, we'll go down and continue this with wine and cheese. Any others? Okay, let's thank Sid again.